Hello everyone, kindly accept my greetings. Myself, Dr. Pankaj Jha, working as an associate professor in Electronics and Communication Engineering Department at IIMT College of Engineering. Today, I will discuss sequential circuit design using CMOS, which is the continuation of my last lecture. In that, I have discussed about combinational logic design. So the content of lecture will be, I will give an overview about CMOS switching, then what is sequential circuit, then CMOS implementation of SR latch using NAND gate, using NOR gate. Further, I will discuss the implementation of SR flip-flop followed by JK flip-flop. So here I'm trying to recall my last lecture in which I have discussed about CMOS switching and making of AND or inverter circuit. Similarly, or an inverter circuit. So in this slide, we will discuss how PMOS and NMOS switching is going on and what are the necessary requirement of voltage at gate terminal so that our MOS circuit can be switched. Okay, so you can see here in first circuit, I have made one PMOS and one NMOS circuit, which is connected with power supply, that is VDD, and NMOS is connected with V ground, that is denoted by VSS. G stand for gate terminal and V output is taken from drain terminal of NMOS. So you can see here G represents gate, S represents source, and D represents drain terminal, where SUV represents the substrate material. So you can recall that PMOS produce saturation region when we are applying zero voltage at gate terminal, and NMOS gets saturated when we are applying high voltage at gate terminal. That is, PMOS will be in saturation mode if at gate terminal input voltage is high. Similarly, NMOS will be in saturation mode when input voltage we are applied at gate is high. Okay. Another thing is PMOS circuit is also known as pull-ups network, and the circuit made by NMOS is also known as pull-down. So in second figure, you can see I have made an inverter where A is the input of PMOS as well as NMOS, because we are giving simultaneously same input at both transistor. So when we are applying zero voltage as an input, PMOS gets saturated, that is VDD will come across Y where we are taking our output, and if A is high then NMOS will be in cutoff mode. That is, when we are giving zero input, the output will be 1. Similarly, when we will provide input high, in that case, PMOS will be in cutoff mode and VDD will not appear across Y, and NMOS will be in saturation mode and it will be connected to ground. So with the help of truth table, we can understand this combination of PMOS and NMOS circuit is acting as a inverter. That is, when we are giving zero input, we are getting high output 1, and when we are giving high input, we are getting output 0. So in short, PMOS, which is also known as pull-up network, will get saturated when we are applying zero voltage or low voltage at gate terminal. Similarly, NMOS, which is also known as pull-down network or pull-down circuit, will get saturated when we are applying high voltage. Now, what is sequential circuit? So sequential circuit are the memory-based digital circuit in which output depends upon the present state inputs as well as the output of last state. And sequential circuit are synchronized by the clock input except latch, which we will discuss further. And most important thing is flip-flop is the basic building block of all sequential circuit, whether it is counter, whether it is register, whether it is asynchronous design. So clock is synchronizing the output of sequential circuit. So let's start from SR latch. So SR latch we can develop with the help of two different universal gate, which is NOR gate or NAND gate. NOR and NAND gate is also known as universal gate because we can implement any circuit using NOR gate or NAND gate. So in this lecture, I will discuss latch implementation by using NOR as well as NAND gate. So this is the circuit of NOR based latch in which R and S are the inputs, Q denotes the previous output, and Qn plus 1, which I have denoted in the tabular in tabulation, is present state output. So when we are applying 0 0 input to NAR gate, there will not be any change. That means latch will produce same output, whatever the value of last is stored in the latch. Similarly, when we are applying S equals to 0, R equals to 1, it will reset the latch and we will get 0 output. And when we are applying 1, S equals to 1 and R equals to 0, latch will be in set condition, and for 1 1 it will be in invalid condition. Okay, let's discuss in detail. Suppose Q is 0, we have taken our previous output is 0 and the value of R and S both are 0. So what will happen? The NOR gate will produce high output if all the inputs are 0. This is the condition of NOR gate in which high output is produced. Okay, so when both input are 0, Q is 0 and S is 0, the value of Q bar will be 1 and Q bar is 1, then 1 and R is having 0 value, so it will produce 0 output. In that case, we will have 0 output again. That means what we have get here is the last output is stored by the latch. Similarly, one more example I will take here. Suppose S equals to 1 and we have considered our last output 0, then it will produce Q bar equals to 0 and 0 will make Q equals to 1. So by this method of working, we can understand the set and reset condition of SR latch. Same circuit we will implement using CMOS implementation. That is, this gate will be replaced by CMOS circuit. So you can see here, I have implemented a CMOS implementation of NOR based latch in which the output Q is connected with parallel with S, that is transistor Q3 and Q4. And since we know that NMOS and PMOS logic are dual in nature, that is, when any network is connected series in NMOS logic, then it will be parallel in PMOS logic. Similarly, if we are performing parallel operation or operation in NMOS logic, then in PMOS design, it will be in series operation. Okay, I think it is clear now. So here we have generated two different equations and the equations are shown in bottom of the table that we have to implement this particular circuit for Qn plus 1 bar. I have implemented S into Q bar, and for Qn plus 1 it will be R into Q bar whole component. Okay, so you can see here that in this circuit, this S and Q, this is Q. Okay, I have denoted here Q, are in parallel in terms of transistor Q3 and Q4. And for PMOS logic, these transistors are in series. Okay, so let's understand with an example. Suppose the value of S, R, and Qn is 0. Okay, so when we apply 0 here and this is the Q, 0 here, that means this will be, this circuit will not operate because this will go in which mode? Cutoff mode. Then VDD will come across Q1 and Q2. As a resultant of this, we will get Q bar equals to 1. And if Q bar equals to 1, you can understand if this is equals to 1, the Q7 transistor will be in saturation mode. That means it will provide a short circuit condition and the output obtained here will be grounded. So we will get Q equals to 0. Okay, that is here we will get Qn plus 1 equals to 0. Let's understand with one more example. Suppose this combination I have taken. So S equals to 0, R equals to 1 and previous output Q is 0. Okay. So if this is 0 and S equals to 0, you can understand again transistor Q3 and Q4 will go in cutoff mode. That means it will be disconnected here. So Q1 and Q2 will be again in saturation mode and Q bar will become 1 high because there is no path to be voltage to be grounded from either Q3 or Q4. So we will get Q bar equals to 1. If Q bar is 1, this will make transistor Q7 in saturation mode and again we will get Q equals to 0. So you can understand that by applying different logic across this CMOS implemented circuit using NOR gate, we can get the desired output as discussed in previous slide. Okay, here I have mentioned these two dot conditions. This is dash dash. That means these are the invalid conditions. So you can recall a SR latch, yeah, SR flip flop will work properly if S and R will producing 0 output. Means S multiplied with R is producing 0 output, then only SR latch, yeah, SR flip flop will work properly. Okay, you can understand this from this table also. Look, 0 into 0, we will get 0. 0 into 0, again we will get 0. 0 into 1, we will get 0. 0 into 0, we will get 1. Sorry, 0. Then 1 into 0, we will get 0. For 1 into 1, we will get 1. In this condition, we are getting both Q as well as Q bar 1, which is called invalid condition of SR latch, either using NOR gate or using NAND gate. Okay. Okay. Next, we will discuss this NAND gate SR latch. That is, we can implement SR latch using NAND gate also, in which position of S and R change here. You can see S is here and R is here. And for this, 0, 0 condition will be invalid state because if NAND gate is having any one of the input 0, the output will be 1. So if both input S and R is 0, then we will get 1 here and Q bar is also 1. That's why in truth table I have mentioned invalid state. Okay. Similarly, if suppose S is 0 and R is 1, in that case we will get 0 output, and S is 1, R is 0, then we will get 1 output, and for 1 1 condition we will get previous output Qn. So set and reset condition will be obtained when S equals to 0, R equals to 1, and S equals to 1, R equals to 0. This NAND gate will also we can implement using CMOS design. Okay, so here you can see in here we are having Qn plus 1 bar equals to R dot Q, and Qn plus 1 equals to S into Q bar. Look, this Q bar is connected with transistor Q3 and Q4. These transistors are in series. You know, for AND operation, NMOS is connected in series. Similarly, if 3 and 4 are in series, its dual network, that is PMOS, Q1 and Q2 will be in parallel. Okay. In opposite side also, 7 and 8 are in series. That's why either 5 and 6 will be in parallel. Okay. So let's examine with one example. Suppose S and R both are 0. Okay. If this is 0 and this is 0, that means what? S will be in cutoff mode, that is transistor Q4 will be in cutoff mode, and Q8 will be also in cutoff mode. Okay. Here 1 will be in saturation mode because this is 0. Okay, and 6 will be also 1. So this VDD will come to Q bar also, and this VDD will come to Q also. That means simultaneously we are getting 1 here also and Q bar 1 also. So this is the invalid condition. That's why I have mentioned here cross. Okay. For another example, we can track with some other values. Suppose S is 0, okay, and R is 1. Let's get with this example that S is 0, R is 1, and Qn is 0. That's we are assuming our previous output 0. In that case, what will happen? This S, okay, S is 0. I'm taking this example. S is 0. It will be in cutoff mode, okay, and Q bar. If Q is 0, then Q bar will be 1. So this will be in saturation. Okay, so this will become in short circuit condition, and transistor Q1 is also in short circuit condition. That means this VDD will come across Q, transistor Q here. Okay, so this Q will be high, and this Q is high. This Q7 will be in which mode? Saturation mode, correct, and R will be also in saturation mode. In that case, this both transistor will be in saturation mode, and this will be grounded. Okay, so Q bar will become 0 here. So for input S equals to 0, R equals to 1, and Qn equals to 0, we are getting high output. Okay. Okay, let's do one more example. Suppose this is the condition. All the inputs are 1. S is 1, R is 1, and Qn is 1. Okay, so this is 1. Here we have assumed that this is 1 and this is 1. Okay, so Q is 1. That means Q bar will be 0. So this will make transistor Q3 to get in cutoff mode, and this transistor is in cutoff mode. That means Q will be 1. Correct? Why? Because this Q2 will get saturated by this 0. Okay, so VDD will come to Q. Okay, and if this is 1, both transistor will be Q8 and Q7 will be in saturation mode, and it is connected with ground. That means Q bar will become 0. So ultimately we will get high output. I think it is clear to all of you. Okay. So now the actual circuit is flip-flop. That is a circuit is improved version of latch. Latch is considered as a label triggered flip-flop. That means output change is not certain. It is unpredictable. Means it is not synchronized. when will be next output is going to change. To synchronize this operation, we are using clock. So clock will produce, yeah, clock will synchronize the operation of latch. So the major difference between latch and flip-flop will be flip-flop is a circuit which consists latch along with flip-flop. And this clock pulse will synchronize the operation of latch. Okay, so this is a gate level implementation or design of SR flip-flop. Here, latch is there. We have discussed this latch, NOR based latch. We have already discussed. Now we are adding these two AND gate with the combination of clock. Okay, this clock is basically enable or synchronize the output. That is when we will get next output is going to decide by this clock. That's why some author, some books are writing this as an enable condition. So I have also mentioned this in this truth table. Clock D stand for disable, then there will not be any change. Latch or flip flop will be stored its previous value when we are providing enable condition. Okay, this is EN. When clock is high, the normal operation of flip flop will go on. Okay, so this one means at the high edge of clock, yeah, high level of the clock, our flip flop is going to change its output. Okay, so when S and R both are 0, 0, we will get previous output. When S is 0, R is 1, flip-flop will be in reset condition. When S is 1 and R is 0, flip-flop will be in set condition. Okay. And again, 1, 1 will be the invalid state because if S is 1 and clock is 1, this AND gate will produce high output. And if any one of the input is high, across NOR gate, it will produce 0 output. So for this condition, I have mentioned invalid state. Okay, so let's get its CMOS implementation. So this is the CMOS implementation of clogged SR flip-flop. Okay, so to understand in better way, we can understand, yeah, we can write first the equations. Okay, equations means how this latch is going to produce output. So for next stage Q plus 1, we are having R multiplied with clock plus Q bar and whole complement. Basically, inverter is not we are adding here. So we will get here complement of the whole output. Okay. Similarly, for Qn plus 1 bar, that means Q bar. Next stage Q bar, we will have to implement S dot clock. That means S multiplication with clock, and further we will do OR operation with Q, that is previous output. Okay, so this is a simpler way to implement any function by using CMOS, whether it is combinational logic design, whether it is sequential logic design. Okay, so let's understand with an example. So you can see here in truth table, I have mentioned clock is in enable condition. That means at every positive edge or at every positive label, this flip-flop will change its output. Okay, so let's start with first combination, that is S equals to 0, R equals to 0, and Qn equals to 0. Okay, so let's understand, if Qn equals to 0, this Q bar will produce high output. Okay, so if Q bar is high, this Q6, which is NMOS, will be in saturation mode, and if it is in saturation mode, it will be grounded. Okay, so whatever the value we are receiving at Q, it will be grounded. That means what? Q will be always 0. Okay, let's repeat once more time. I'm saying just I'm checking the value of Qn. Qn is 0. So if Qn is 0, this Q and bar, yeah, Q bar will be 1. And if this is 1, this make transistor Q6 in saturation mode. And if this is in saturation mode, it will connect it with ground. So whatever the value of R, Ck, it will produce always 0 output. Understood? Okay, let's give some another example. Suppose clock is 1, obviously, S is 1, R is 0, and Qn is also 0. That means this is 1. Clock will be at 1 position, high position, because it provides enable condition. This R is 0, okay, and this clock is at again 1 position. So what will happen? This S is 1, it will make transistor Q11 in saturation mode, okay. Clock is at enable condition, that means it will make transistor Q12 is in saturation mode. If both transistors are in saturation mode, that means what? It will be in short circuit condition and provide a ground path. So whatever the value of Q bar is will be grounded. So Q bar become always 0. Okay. So if Q bar is 0, now understand, if Q bar is 0, then transistor Q6 will be in which mode? Cutoff mode. Very good. And R. R is, since R is 1, okay, R is 1, that means, sorry, R is here 0. So it will be also in which mode? Cutoff mode. So both transistors are cutoff mode. That means we will get here what? High output, because this A will be in saturation mode, because this is 0. So Q3 will be in saturation mode and R is 0. So Q1 will be saturation mode. So VDD will reach to Q. So for condition 1, 0, 1, we will get high out. Okay. Okay. One last condition I will discuss, in which we are getting invalid condition. Here I have represented by don't care. Okay. Let's suppose all are R is 1, clock is 1, S is 1, clock is 1. So if both transistor Q11, Q12 will be in saturation mode. Similarly, Q4 and Q5 will be in saturation mode. If both are saturated here, this Q will be grounded. If 11 and 12 transistor are in saturation mode, again this Q bar will be also grounded. At the same time, we will get 0 output at Q and Q bar both. That's why we are saying this is the invalid condition. And I have discussed earlier that SR latch, SR flip-flop will work properly if the value of S dot R equals to 0. Understood? Okay. So let's proceed further. To the problem arises in SR flip-flop is when we are applying high output at both terminals, that is S equals to 1 and R equals to 1. In that case, circuit goes, yeah, produces invalid output. So JK flip-flop removes that problem. Okay. So first important thing about JK is the 1-1 condition is a problematic situation in SR latch or SR flip-flop, that will be removed by JK flip-flop. That's why we are using JK flip-flop for more precise designing. Okay. So what will happen when we are applying 1-1? The output will be complemented. That is also known as toggle condition. That means if previous output is 0, now it will become 1. If previous output was 1, then we will get 0 output. Understood? So from this table, you can understand again when clock is in disable condition, D stand for disable condition, no change of output is there. Okay. Whatever the previous output will be stored by flip-flop. When we are applying 0-0 condition and clock is enabled, in that case, no change is there. We will get Qn as a output. When J is 0, K is 1, we will get 0 output. That is flip-flop will be in reset condition. And when J equals to 1, K equals to 0, that is flip-flop will be in set condition and will produce high output. And if both inputs are 1, 1, then flip-flop will toggle its previous output and become QN bar. Okay, so this will be the truth table of JK flip-flop. So here from the circuit you can understand we have used here NAND gate, 4 NAND gate to implement JK flip-flop. Okay, so this is the latch, NAND latch, and additional 3 input NAND gate we have used to design this, in which what we are doing exactly, we Q bar is fed back to J. This Q bar is taken as an input to this NAND gate, and Q is taken as an input to this NAND gate where K is connected. Okay, so if we try to write the equation, okay, so how we will write for Q, this Q, we will write J into clock into this Q bar. Here I have written J into clock into Q bar, and this is NAND operation, so I have mentioned here one complement. This output of NAND gate will be further multiplied by what? Q bar. And since it is again NAND gate, the whole function will be complemented. I think it is understood to all of you that J dot clock dot Q bar complement is multiplied with Q bar whole complement. So basically, this is the function we will have to implement when we will do CMOS implementation of the circuit. Similarly, this Y2, okay, Y2 means Q bar. What we did? K multiplied with this Q and multiplied with clock. K dot clock dot Q complement, since it is NAND gate. Further it is multiplied with Q and whole complement is there. Understood? So the output of Q bar will be K dot clock dot Q complement multiplied with Q, whole complement is there. Understood? Okay. Now, when we will implement this using CMOS, this will a complicated function. So what I did a simplification of the function using De Morgan's. So you know De Morgan's theorem, that is A multiplied with B whole complement will be A bar plus B bar. Similarly, A plus B whole complement can be written as A bar into B bar. So using De Morgan's theorem, a simple output expression we have found here, that for Q next stage Q, we will have J bar plus clock bar plus Q multiplied with Q bar and complemented with complete complement. Similarly, Q bar will be K bar plus CK bar plus Q bar multiplied with this Q, and whole complement is there. So in previous slide, again, understood the problem. There is 3-layer complement function in one output. Q bar is there, then J dot clock dot Q bar complement is there. Further, it is multiplied with Q bar and complement is there. So to simplify this, what I did here, simply I did a multiplication conversion into addition with the help of De Morgan's theorem. So by using De Morgan's, we have get these expression, and this is the simple implementation of JK flip-flop using clock. Okay, so the complicated equations can be miniaturized, simplified by using De Morgan's so that the circuit implemented by CMOS will not get complete. Okay, so let's start with example. Clock are in enable condition if all inputs are 0. Look, if all inputs are 0, what will happen? This J bar is here. That means if it is 0, here it will be 1. Okay. K is as it is. So K bar, it is also here. What is it? 1. Okay. So what will happen? This function, this J bar and K bar, that means transistor Q6 and transistor Q14 will be in which mode? Saturation mode. Okay. Now, if I have taken Q equals to 0, then Q bar will be 1. So if this is 1, this Q5 will be also in which mode? Saturation mode, and J bar is also producing saturation for Q6 transistor. So transistor Q5 and Q6 both will be in saturation mode. And if both transistors are in saturation mode, whatever the value is here will be grounded. So it will be always 0. Understood? This will be always 0 because 5 and 6. By checking only 5 and 6, we can conclude that this Q will be 0. Okay. Here, if this is 1, it will make this transistor Q13 in cutoff mode. That means this circuit is isolated. So VDD is coming across Q bar but not going to ground. So that means Q bar will be 1. Understood? Let's give some another example. So let's suppose I have taken this example. 1, 0, 1. That means J is 1, okay, K is 0, and Qn bar. Qn is 1. So if this is 1, okay, it will be 0. So if Q bar is 0, that means Q5 will be in cutoff mode. Okay, so Q5 will be in cutoff mode. That means whatever the value is appearing across Q will be remain same. Why? Because here it will be in cutoff mode, that it will be in open circuit condition. So this value will not move towards ground. Understood? Okay. And what will the value of Q? Q bar is 0. So Q bar is 0. That means Q4 transistor will be in saturation mode. So this VDD will appear across Q and we will get high output as a result. Okay, understood? So by this circuit, we can implement our CMOS logic design of JK flip-flop. So we have discussed. I'm concluding the lecture here. We have discussed what is sequential circuit. Okay, NAND based latch and NOR based latch. That is the building block of any sequential circuit, any sequential design. Okay. Further, since latch is having the synchronization issue of output, we move towards flip-flop. We have implemented a flip-flop, SR flip-flop and JK flip-flop. The basic difference between latch and flip-flop is in flip-flop, there will be a clock circuit which is going to synchronize our output. Means when the next output is going to change will be decided by the clock itself. Okay. So first we have discussed about SR flip-flop. In SR flip-flop, 1-1 condition is producing invalid output. Okay, invalid output means when Q and Q bar both are having same output, we will say it invalid output. To remove this condition, okay, to improve the circuit of SR, we have implemented JK flip-flop in which the condition of 1-1 which was invalid in SR latch is removed here, and for 1-1 condition output will be the complement of previous output. Okay, so that is known as toggle condition. So for 1-1 condition, JK flip flop is producing toggle condition. So all the possible states or combination of input is addressed here using JK flip flop. That's why in most of the sequential circuit design, we are using JK flip flop preferably, okay? And specifically for counter designing, only JK flip flop are being used, whether it is synchronous counter or it is asynchronous counter. And this we will discuss in next lecture also. Thank you.